So this is number 25 on both tests. So we have a regular pentagon with the areas given, and we are cutting like the pentagon by taking one vertices and connecting with the center of the pentagon. So we are doing for all like vertices, and we are gonna make another pentagon. And what we want is the area of that new figure. Okay. So like let's see how that's gonna look like. First things first, let's say if you connect these two guys. Okay, so you're gonna get right in the middle as the like cutting line, so which will be perpendicular to the this segment. So if you were to draw that, so it will be something like this. Okay, and if you do the same thing with the all other sides, you are gonna see something similar. Okay, and then if I do the same thing with the other sides, so again, it's not perfectly drawn figure, so I'll try to visualize. Okay, and then we got that piece. And the last one might be something right here. Okay, so I hope that makes sense. Like what we are gonna get basically the region right here. Maybe I should label separately. So we are gonna get the area of this pentagon, this inside one. Okay, so to do so, you know, since we are doing this for a regular pentagon, the middle pentagon right here and the larger pentagon right there is actually similar. Okay, so which is gonna be useful at some point of the solution. So let's try to see how that looks like. And since this is a perpendicular, so that will be a 90 degrees. And I do know this is gonna be same as this guy because of that is the point that you're like reflecting. Okay, so that is gonna be useful as well. So what we want is the some of the other information. You know, if I take this center point and connect the center of this segment, it has to go through this midpoint because it is symmetric. So let's do that as well. If I draw that, so I will get this triangle. And this is a nice right angle triangle. And if you divide like 360 by like 5, you get like exterior angle, which is 72. Interior will be 108. So that means this is 54, right? And then this is gonna be 90. This is 36. Okay, so we have 36 and 54, which actually why I draw like add these to like identities, which is gonna be useful. Okay, so what we have now, there's a right triangle, and I said at the beginning that the smaller pentagon and the larger pentagon are similar by symmetry. So which is why I can just find the ratio of the similarity and use that to find the ratio of the areas because we are given one of the areas. We don't really want to find each side length and like find the area from there, which is going to too tedious work. So which is why let's find the ratio of the sides. So if you look at the like the distance between the center to this point, which is actually a distance that will be equal to the when you draw this every side of the smaller one. If I call this is x, so that would be x as well. And if I know this guy somehow, if I call this is a, let's say this is h, then OH is actually corresponds to this x distance because that is going to be height of those two like pentagons, I would say. If you were to draw like a triangle like this, okay, so this will be height of this triangle will be x, and OH will be height of this triangle. Since they are going to be similar, ratio of the heights would be ratio of the similarity. Okay, so then let's write something to get there. Okay, so if you want to write the x divided by like OH, that is the ratio of the similarity, right? So let's go ahead and do that. But how do I relate those? Like I can take the sine of 54 because that will give me what I want. So the sine 54 is opposite OH over hypotenuse, which is going to be 2x. Okay, so that is good, but what we want is the x over this one or this over that one. So to get the ratio of the like similarity. So, but in order for us to do so, we have to know the sine 54. So which is why it's gonna be tedious like part actually of this solution to get the value of the sine 54. Some people may remember this guy, but it is not too common. So which is why I will just use the two famous like identities to get this sine 54. But at the same time, you know, we know that like sine 54 in this triangle is the opposite divided by this. If I take cosine 36, that will be equal to as well. So which I'm gonna use it. So sine 54 is equal to cosine 36. So let me write down. But if I want to remember these angle sum and double angles, you know, the sum of two angles, when you know the cosine, you can just kind of expand those way. And then the double angles are these two. So it's good to have the double angle, but why do I need to use those? You know, this is like 18 times 2, this is 18 times 3. So these two can be related if you want to write both of them in terms of like sine and cosine, like 18. So that would give us some idea. So which is why I'll try that, but to do so, you know, the cosine 36, like we don't really have nice relation with that, at least for this one. So which is why instead of using this for now, I'll take the like cosine 54, because in that triangle, cosine 54 would be same as sine 36. Because sine 36, like I'm gonna use double angle to get this use this relation. So cosine 54, I'm gonna use this guy first. So like I'm gonna write 54 as 2 times like 18 plus 18, or I can write cosine 36 plus 18. And then instead of sine 36, I'm gonna write 2 times sine 18 times cosine 18. Again, if you are not familiar with this might be a bit confusing. So I'm just using the identities, which is two famous identities. So if you are not familiar with this, maybe it's good to start with those like studying. So now if I expand this guy using this identity, so you will get cosine 36 times cosine 18 minus sine 36 times sine 18. And that is equal to 2 times sine 18 and cosine 18. Okay. And if I expand now cosine 36 by using the same thing one more time, or this guy, I can use it. But there is a cosine 18 right here. This is sine 36. Maybe I can expand this as well first before we like expand this one. Because this guy, if I expand this, so that will be 2 times sine 18 cosine 18. So we have cosine 18 in this product. We have cosine 18, cosine 18. So if you divide both sides by the cosine 18, so we are gonna cancel this guy, and cancel this guy. So now we may expand cosine 36, like maybe by using this guy, because I'm gonna write everything in terms of sine like 18. So if you replace this with this guy, like instead of alpha, you can just say 2 times 18, which is gonna give me this one. So 1 minus 2 times sine squared 18, okay, that's cosine 36, minus 2 times sine 18 times sine 18, which is going to be 2 times sine squared 18, is equal to 2 times sine 18. So like if you want to substitute at this point, you may just do like sine 18 equals maybe like k. So that will be -2, which is -4. If you pull everything on one side, so that should be 4k squared and plus 2k minus 1 equals 0. And if you use the quadratic or like maybe complete square, so you are gonna get k, which is gonna be sine 18, is equal to our like sine 18. Let me check that one. Yeah, if you use the quadratic formula, you are gonna get like -1, I guess, plus root 5 over 4. Okay, so you can double check. So if you like just use the quadratic formula, so you should be getting this guy. And as soon as we got sine 18, we want to get, like, use this guy to get what we want, which is sine, like, 54. But how do I get that? So sine 54 was the same as cosine 36. If I know cosine 36, then I can get this one. But I do know cosine 36 can be written as 1 minus 2 times sine squared 18, which is, we know the sine 18. So then, like, sine, let me use different color. So the sine 54 is equal to cosine 36, which is going to be 1 minus 2 times sine squared 18. If you plug this into this guy and simplify, so you will actually get sine 54 as 1 plus root 5 over 4. And this is the, like, common, like, number. So if you kind of remember the golden ratio thingies, so you may remember this one as well. But I'm gonna leave it for you to explore the golden ratio with the, like, these angles. But for now, so you can just explore it on your own. But we got the sine 54, which is like we were looking for. So we are almost there. So the question was asking us to find the areas, right? So the area ratios, maybe I can use right here. So the area ratios is just the square of the sideline. So the one side, like, since we know the area of the largest, like pentagon, which is OH, so I'm gonna write here OH divided by, like, if I call this is like KOK, this is my ratio of the corresponding part. If you square this is gonna be area ratios, which we are given 1 plus root 5 for the larger pentagon. I'm gonna call the area of the smaller pentagon as A. So OH is basically 2 times x times sine 54. So 2 times x times sine 54 divided by OK is just x, which is really nice to cancel these guys. And we are gonna square this. That will be 1 plus root 5 over A. So what we want to do now, instead of sine 54, we are going to plug 1 plus root 5 over 4 right here. Okay, so that will be multiplied by 2 if you do. So you will get 1 plus root 5 over 2 to the second power. So it will be 1 plus root 5 over 2 to the second power is equal to 1 plus root 5 over A. If you expand this and cross multiply, you are going to able to get the A as root 5 minus 1. And that is the area of the smaller pentagon. So it's kind of too, like, much like working, at least if you don't really know these identities, or if you cannot really see how to apply that identity in our problem. So that might be a bit challenging, but that's the last question on the test. So that was the point. So I hope that makes sense. So I highly recommend you to go ahead and do these steps on your own. And I just skipped the calculation part. So you have to actually check those numbers to make sure you actually understand the solution. Okay. So I hope that is clear, and I'll see you in the next video.